Hi, this is Alex Yazdani. This is a demo video, the second demo video for our final project in EE533 in the spring of 2025 with Professor Young Cho. I'm Alex Yazdani. My lab partners are Tim Liu and Szymon Gorski. So this week what we were working on was an accelerator to encode image data for our project, and we already had the floating point multiply accumulate logic generally, but this week we've actually pipelined everything and made it a processing accelerator with iMemory and dmemory and all of that, and then implemented it on the FPGA and actually got it working. So first I'll just go into the demo and then I'll kind of give a little bit more background data just to help it make sense. So first we just want to load the bit file, and then we want to program it with I think maybe it would help if I pull this up right here. So first we're gonna program iMemory. This is our pipeline. So we have an iMem with a PC. We have two data memories instead of a register file, and that's because we want the network to actually put packets in. Then we have a multiplier accumulate unit. We actually have another pipeline stage in here. It just hasn't been updated yet. And then a dmem at the output that we store our data in, and then that goes back into the network. So first we want to load instruction memory. So we just have imem.text, and then we can verify that that loaded in properly. Yep. And then we want to load in one of the dmemories. So first we're loading in the batch data, and then we'll do the scalar data next. Functionally, these are just two copies of the same, but one in practice, one is a scalar and one's our image data. So just load both of those data memories and then just verify really quick that those loaded properly. We can see from the dumps that they did. And then, so yeah, our data memory is loaded with our image and scalar data, and our instruction memory is loaded with the program. So now first we'll just do a dump of this encoded memory, and we expect it to be empty right now. So yeah, it's all zeros or uninitialized. And then if I just do run, this basically enables the PC, all of the stage registers, and it just lets the kind of pipeline execute. And then stop, that shuts it off. And now if we dump that again, we can see that we have things written now. So this says 0, it's really like an XXX. It's just nothing has been written to it yet. But here, the way we've written the program is it writes to every 8 addresses, or every 8th address. So this is the first result of the multiply accumulate. This is the second, etc. And we know that this works because we have the control here. So this Python script I have actually generated a bunch of random decimal numbers, and then it converted them from decimal to floating point, like binary format, and then we use those output or those generated files. It's just a list of binary numbers as the dmem files to load into here. So first I executed it in a simulation before I started this video recording, and then afterwards I implemented it on the FPGA, and we can see that the results are the same. If I data encoded. So here, first one is 5D44 and then 597F. This is the output from the Python, like completely ideal simulation. 5C34, 5C7F, 5C, 5C2B, 5A3D, 5B90, and 5CFA. So we see that this does match our ideal simulation, and just for a sanity check here, we also multiplied the decimal. We generate the decimal numbers, convert them to binary, then use our pipeline to basically multiply and accumulate them, and then store that in DMEM. And then we take that DMEM and then we convert it back to floating. And then on the side, we also multiply the decimals just in Python. And then we compare the expected to the actual simulated that's been converted back from binary into a decimal format. And we can see that the errors are pretty low. It's all less than, like, I think the highest is 0.29. So it's all less than 1% error. So yeah, that's pretty good. So that's all for the demo. So we have this entire pipeline working here. And so, yeah, the next step is basically just integrate the network into this. We're still working on that. So yeah, that's all. Thank you.